Okay, let's get started. Good afternoon. So I realize this course has been a real marathon, but we're reaching the end. Uh, and just for those of you who may not know, being outside the country, this week there's only one lecture. That's today. Wednesday and Friday are off because of the Thanksgiving holiday. And then we'll have two more lectures next week, and that'll be the end of the course. And of course, there are corresponding discussion sessions at 9 a.m. the next morning, including one tomorrow. And also tomorrow, there'll be a section where I think how you will cover basic aspects of non-abelian statistics in the Ising topological order phase. All right, so today we are going to continue our discussion of dualities. And the particular duality we have focused on so far has been the duality of the XY model in 2 dimensions, which turns out to be remarkably similar to the duality of U1 gauge theory of the type you meet in many spin liquids in 2 dimensions. Okay. All right, so let me just summarize in pictures, shall we say? Well, yeah, what we achieved so far. So let's see. So we started with the 2D XY model, and we ended up with this dual vortex theory, which is a theory for some field phi, which initially doesn't have much of an interpretation, physical interpretation, at least in the context of the XY model. And it has a Sine-Gordon form in the terms of the theory of the field phi. And you can think of physical interpretation of phi is that e to the 2i phi in our normalization is a vortex operator. Now, another useful form of the theory, which I didn't mention yesterday, also makes the physical interpretation clearer. So what you do is you start with the Sine-Gordon form, and just expand it expand. So here's the theory I just mentioned, written out explicitly. And then you just take the partition function and you expand it in powers of y. So when you expand it in powers of y at every order, so at the 2nth order, you'll have 2n cosines out in the whose average you have to evaluate in the Gaussian action, because you expand this out and you keep the Gaussian action up here. And when you do that, turns out you can compute that correlation function in closed form. This is in fact one of the homework problems where you compute the correlators of arbitrary numbers of exponentials in this simple Gaussian action. Okay, and what you get, well, first important thing is that when you expand the 2 phi, the cosine 2 phi, you can write it as e to the 2i phi plus e to the minus 2i phi. So the way we write this is we interpret this term as a charge. I'll become clear why I call it a charge, p equals 1. And we interpret this term as a charge we call p equals minus 1. So you have a bunch of charges. In fact, you have an arbitrary number of these charges And you can think of this partition function as just the grand canonical ensemble of a gases of these charges. So there's some arbitrary numbers. Clearly, in thermodynamic equilibrium, you'll be dominated by some mean density, just like any grand canonical ensemble. And the charges come in equal and opposite signs. So the first thing you find when you do this integral, and this is something you will find out in the homework, is that unless there's global charge neutrality,